Hello everyone, my name is Yan Ding. I am an associate professor from NUDT. Today, I'd like to introduce our work, and the subject of my presentation is TZ-IMA, supporting integrity measurement for applications with ARM TrustZone. My presentation is divided into four main sections, namely background, architecture, evaluation, and conclusion. First, let me introduce the trusted computing technology and integrity measurement architecture. Trusted computing aims to build trust in computer systems. It uses a hardware TPM chip as the root of trust. TPM is short for Trusted Platform Module. Then it establishes a chain of trust, which measures components layer by layer during the system boots, from BIOS to bootloader to OS kernel. Based on trusted computing, IBM Research Center proposed Integrity Measurement Architecture (IMA) in 2004, which first extends the trust measurement concepts from the BIOS all the way up into the application layer. There are two main mechanisms in IMA, named remote attestation and local appraisal. For remote attestation, while booting, IMA measures all executable, loadable kernel modules and their configuration files before execution. The computed hashes are managed by a list called measurement list, and each measured hash values is extended into the PCR10 in TPM, making a new hardware-protected hash chain. The IMA appraisal mechanism supports local integrity validation and enforcement. It stores the reference value of the application hash in the local system. The measurement value is compared with the reference value each time when the application is loaded. Only when the reference value exists and matches with the measurement value, the execution is allowed. However, traditional operating systems are complex and may contain many potential vulnerabilities. If the sensitive data used in IMA is leaked or modified by the attacker, the protection mechanism will lose effectiveness. Moreover, as a coprocessor, TPM is low, resource limited, and must be deployed specially on the computer system, which limits the usage of IMA. Recently, T technology has been widely deployed on servers, mobile phones, and internet devices. T is short for Trusted Execution Environment. The more famous Ts are Intel SGX and ARM TrustZone. It guarantees code and data loaded inside to be protected with respect to confidentiality and integrity. Our design is based on ARM architecture. The T for ARM devices is called TrustZone. TrustZone divides one system to two worlds, the normal world and the secure world. The normal world, rich execution environment, runs rich OS like Linux or Android. It has three layers. one for hypervisor, one for kernel, and one for application. The secure word T or TrustZone has 2 layers, one for TEOS and one for TE applications. The monitor model or EL3 is used for switching between the 2 words. It is also part of the secure word. The switching is done through SMC instruction. TrustZone provides an isolated environment with higher privilege than the REE. And prepared with TPM, TrustZone is a more flexible approach to realize integrity measurement. Based on ARM TrustZone technology, we propose TZ-IMA, a security-enhanced solution to verify the integrity of applications. Here is the architecture of our design. Compared with the original IMA, the components of TZ-IMA are across words. Integrity measurement hooks are intercept the user's execution in sensitive applications in the normal world, and 4 security modules to provide integrity measurement and protection services in the secure world. In the normal world, TZ-IMA reuses the hooks in the original IMA. These hooks are mainly called by the system calls, such as open, mmap, and so on. In the secure world, first, TZ-IMA constructs a measurement agent. It is used to calculate the hash value of the application when the application is loaded into the memory. Third, vPCR model is to support remote attestation. A measurement list is constructed in the normal world. The PCR register is virtualized to protect the integrity of the measurement list. Meanwhile, vPCR encrypts measurement value with mlist key to ensure the confidentiality of the mlist. A challenger can judge whether the remote system is trusted by validating the vPCR signature and the measurement list. Fourth, key manager model is responsible for managing 3 keys used in TZ-IMA. The appraisal key and mlist key are 2 semantic encryption keys and used to encrypt the reference value of the application hash and the entry of measurement list, respectively. The platform identity key is a private RSA key used to identify the attesting system's TrustZone. Based on the 4 security models, TZ-IMA provides 2 mechanisms, appraisal and attestation, to protect the integrity of applications running on the computer. For both 2 mechanisms, when the process opens and executes sensitive applications, the query is captured by the hooks. And the measurement agent in TrustZone are called to calculate the current hash value of the application. The appraisal mechanism can detect whether the application has been altered accidentally or maliciously by appraising an application's measurement value against the reference value. The workflow of application integrity verification is as follows. First, the normal world operating system retrieves the extended attribute value of the application and passes the reference value to the secured. Here, to prevent the reference value from being tampered with, TZ-IMA uses semantic encryption algorithm to protect the reference value, and the semantic encryption key is called appraisal key. To enhance its security, the appraisal key is saved to the trust zone, and a comparison model is constructed in the secured. Thus, during the whole lifetime of TZ-IMA, the appraisal key is isolated from the completed execution environment and will never be exposed to the normal world. After TEE receives the reference value, the comparison model loads the appraisal key from the key manager to decrypt the reference value. If it matches the measurement value, the integrity verification is successful and the application can be executed. Otherwise, the authentication fails and the access is denied. TZ-IMA attestation aims to provide a measurement list including the application execution status of the remote system and enable the challengers to detect whether sensitive applications have been modified or executed by malware. The workflow of an attestation mechanism can be seen from this figure. Before the application is executed, the measurement agent calculates the file hash and extends the measurement value to vPCR model. vPCR model is virtualized to avoid the measurement list being tampered by an attacker. To guarantee the confidentiality of measurement list, TZ-IMA generates a mlist key in the key manager and leverages the key to encrypt the measurement value. Then, TEE returns the encrypted measurement value to the normal world OS to store the encrypted file hash. The vPCR model, the vPCR value, and the measurement list can be used to prove the integrity status of a remote system. This manner ensures both the integrity and confidentiality of measurement list and save the storage space. Based on TrustZone provided by ARM CPU, TZ-IMA leverages Trusted Application (TA) to virtualize a vPCR model. vPCR is a 160 bits virtual register, which is set to all zeros when the computer is initialized. After booting, the vPCR value is updated in an extended manner shown as the equation. That is, starting from the first component, calculating the integrity measurement value of the component with the existing vPCR value, perform a hash operation, and then store the result back to vPCR. At the same time, vPCR only supports reset and expansion commands and cannot roll back to the original value at a certain time. The interfaces provided by vPCR module is shown in the table. The normal world has no way to modify the value of vPCR because it is safe in TrustZone and can be only called by measurement agent. Thus, vPCR module can protect the integrity of mlist. When a challenger initiates an integrity verification challenge, The system needs to provide an integrity report generated by a trusted entity. The figure shows the procedure of remote attestation. In step 1, the challenger creates a non-predictable nonce and sends a challenge request message to the attesting system. The nonce is generated to protect against a replay attack. In step 2, the attesting system loads the platform identity key into TrustZone, and the secure word signs the vPCR value and the nonce with the private key. In steps 3 and 4, the normal word OS retrieves the signature and the mList key from the trusted OS and the merriment list from the file system, respectively. Then, the attesting system responds with a challenge response message to the challenger, including signature and merriment list in step 5. After the challenger receives the response, it first retrieves a trusted certificate in steps 6 and 7. The PIK certificate binds the verification key to a specific system and states that the related secret key is known only to a specific trust zone. Finally, in step 8, the challenger verifies the signature and leverages mList key to decrypt the merriment list entry. If the signature is valid, then the vPCR value is trustworthy and can be used to verify the integrity of the merriment list. The integrity of the attesting system can be verified by comparing the merriment value of each merriment list entry with a list of trusted merriment values. A prototype of TZ-IMA is implemented on a FITM ARM development board. Linux is modified as the normal world OS kernel, and OPTE is used as the trusted OS. We evaluate the performance of TZ-IMA in 3 parts: system boot time, system overhead on Unix bench, and LM bench. The boot time includes the time spent in initializing the kernel and the user space. This table shows the IMA and TZ-IMA boot time evaluated in the appraisal scenario and the attestation scenario. Original system refers to the system without application integrity protection, whose boot time is 27.98 seconds. For the appraisal scenario, the default policy is to verify all applications owned by the root. The system verifies approximately 6,000 files during boot time. It shows that IMA takes 29.27 seconds to boot, and TZ-IMA takes 29.46 seconds to boot. And the overhead of TZ-IMA appraisal is approximately 0.6% higher than IMA appraisal, which is mainly brought by the word switching. For the attestation scenario, TZ-IMA booting takes 29.49 seconds. In comparison, the time of TPM PCR extension is much longer. A previous study shows that TPM 1.2 takes approximately 27 milliseconds to perform PCR extension per file. While booting, IMA attestation mirrors 3,300 files, resulting in approximately 90 seconds of boot time, which is 3 times greater than the booting without IMA. However, based on TrustZone, the overhead of TZ-IMA attestation brought by the word switching and the vPCR extension is only approximately 0.1 second, decreasing by 75% compared with IMA appraisal. Unix Bench is a tool for testing the performance of Unix systems. The result of performance tests is an indexed value, which is obtained by comparing the test result of the test system with the test result of a baseline system. The influence of TZ-IMA for most test items is less than 1% than the original system, and the performance of 2 items, Excel throughput and shell scripts, decreased by approximately 2%. The result is reasonable because the overhead is mainly caused by the frequent program execution. More time is spent on hash value calculation and word switching. LM Bench is used to test system call overhead of TZ-IMA. The normalized overhead of runtime performance of the appraisal scenario and the attestation scenario compared with that of the original system is illustrated in this figure. TZ-IMA mainly influences open-close, mmap, process fork, and executive because TZ-IMA performs security check on these system calls. TZ-IMA does not remarkably affect the performance of the syscall read, write, and state. For most test items, the overhead of a single operation is less than 0.1 microsecond compared with the original system and can be neglected. Here is the security analysis of TZ-IMA. There are also some security limitations in TZ-IMA. First, the hook point check may be bypassed during the runtime. This limitation can be fixed by setting the kernel code segment to read-only and depriving the kernel's ability to control certain privileged system functions. In this manner, the check of TZ-IMA cannot be bypassed. Second, there may be bugs in trusted kernels, and attackers may leverage such vulnerabilities to obtain data from TE and even destroy the RE kernel. Defending against these attacks is not the goal of TZ-IMA. Researchers are focusing on various methods, including stronger isolation and formal verification to solve these problems. Here comes to the conclusion. We proposed an integrity verification method for applications based on TrustZone technology. We propose a remote attestation scheme that enables challengers to validate the integrity of applications running on the computers. A prototype is implemented on an ARM development board, and the evaluation results demonstrate that the system has small performance overhead. That's all. Thank you for listening. And any questions?